Hello, I'm Eric Peterson, Innovation Manager at Corporator. The reason I've prepared this video is because it's been very difficult for me to find good training or informational material, on video at least, related to how Monte Carlo simulations are used to calculate value at risk. You can find good definitions of value at risk related to investments, and you'll usually see some definition that looks like this, where the main points are that it's a measure, it's an estimate, it's not an exact science, it's based on loss, and that there's some stated level of certainty involved. And of course, since it's risk-based, it has to be set against some sort of time window. So it's based on some reporting period. In the risk world, it's usually based on a portfolio or a group of potential risk events. It's not intended to be used for single risks. In fact, it would be useless on a single risk. We cannot predict whether or not a single risk is occurring. It's also not very useful on small numbers of risks, as we'll see later. Another key point is that the potential loss needs to be quantifiable. You cannot use it for risk impacts that are qualitative or descriptive. We need numbers, and these numbers need to be expressed as a potential financial loss. There's also a time window, since the probability of a risk event occurring is bound by time. So it's like again, it's a year, 2 years, something like that. It's generally not a very short time window. It's usually something somewhat substantial. And then when we talk about the certainty of the result, I'll explain that later, but we really mean is how certain are we? Are we 50% certain, or are we 95% certain? And this is actually quite quantifiable, as we'll see when we get into it. And the results alone are meaningless if we don't measure them within some sort of financial context, such as earnings or some other financial metric. So we briefly discussed what it is, but why use value at risk? Some companies are simply required to report this by law. For example, in Germany, companies that are listed on the stock market are required to aggregate risks that pose a threat to the overall resilience of the company. And the point is, it's important that these companies continue to exist. It's important for shareholders, employees, customers, and there are regulations put in place to promote good business practices and to try to reduce risky business practices. But I guess the final point is that when you start measuring value at risk, it anchors the overall risk management function within your company to a higher purpose. It helps people understand the importance of the risk framework and the related activities. So I'm going to jump right into Monte Carlo simulations, explain what Monte Carlo does and why it is used. But first, a bit of background. And this is really the definition of Monte Carlo. It's a model that predicts the probability of different outcomes by using random variables. And that might sound a bit crazy at first. I mean, why would we use random values when we are working with a quantifiable model like value at risk? How can introducing randomness possibly help us? And I think to begin with, we need to take a look at how risk is typically reported. If we have a risk event, we typically look at it from 3 different dimensions. You have the time frame, so that's that time context. Again, normally companies use a year or a 2-year window for looking at a risk event, but we need some time window for the probability to mean something. The probability and the time context go hand in hand. If you say something has a 20% likelihood of occurring, what does that mean? Is that in the next 100 years or the next year? But we need a time frame. And we also need an estimate of the financial impact. This would be the monetary loss that the risk event will bring. Often this is also an estimate. And some of these financial impacts might be fully known, might be a fixed value. It might be rare in practice with actual companies, but there are cases where you might know the exact financial consequences. But most of the time, the potential financial impact is not fully known. It's partially known. So companies often express this within bandwidths. So this would be like a minimum and a maximum value, and then the reality would be somewhere in between. And you can think of it something like this: if you have an insurance policy on your vehicle, your potential loss in the event of a collision could be based on your insurance deductible. So if you have $1,000 deductible, that would be your max, and the minimum might be zero, like if another driver is at fault. But the point is, the financial consequences are often in bandwidths, and we'll discuss how these are distributed on those bandwidths a bit later. But because sometimes there might be also a most likely value or an expected value. This is another term that you start to hear in Monte Carlo simulations. It's the term distribution, and that defines how these financial impacts are distributed. And for the sake of simplicity, to start with, we'll focus on a uniform distribution. That's the simplest to understand. These are the normal random values that people are familiar with. If we have a range between 0 and 100, we are just as likely to receive a value of 0 as the value of 100 when a random number is generated. Every value in between the minimum and maximum has an equal chance of occurring. So in this example, I have a single risk, and I just want to focus on the distribution here. But my range is between 0 and 100. And that's just to keep things very simple and easy to understand. This means I will generate, in a Monte Carlo simulation, we're going to generate 100,000 random values between 0 and 100. And I'll explain a little bit about how a histogram works here. But in a histogram, I'm going to be dumping them into buckets. And I have 50 of these buckets going across the bottom. Basically, the first value, it's like between 0 and 2, and then 2 to 4, and 4 to 6, and so on. But we have 50 buckets, and they express all the values, possible values between 0 and 100. And you can see we get approximately 2% of these in each bucket, which makes sense. And it just shows that they're uniformly distributed, more or less. I mean, it's random, but it's pretty much a straight line across the top. And then if I want to report on a confidence level here, like if I want to be 95% confidence, that's something I decide. I could decide I want to be 90%, 85%, 50%. It doesn't really matter, but it's something I decide. If I want to determine the value at risk at a particular confidence level, what we'll be saying is if I want to be 95% confident, I have this spark line here at 95%. It means 95% of my values are at this level or below. So this is a result that it basically comes from a percentile. And what a percentile means is that we just basically stack up all of these random values from 0 to 100, and we stack up all 100,000 of these up. And we look at the 95th percentile in order, so that 95% of those values are at that level or below. So if we have 100,000 values, I would select the value at the 95,000th position. And since our data here is all neat and tidy, that value should be exactly 95, which makes sense. If my range was instead of between 0 and 100, if it was between 0 and 20, then my value at risk would be around, or the value at the 95th percentile would be around 19. And so far, this is really simple math because we're just dealing with one item. This is just another little example of showing percentiles. If you want to show the median or the midpoint, you can see on the mouse over it, it's 50 at the 50th percentile, which also makes sense. Again, one simple example. But what will happen if I add one more risk to this with exactly the same bandwidth and the exact same distribution? What do you suppose will happen? So not one risk, but we're going to put two risks and we're gonna stack them on top of each other. Do you think the value at risk will double? So it'll go from 95 to 190? Let's just take a look here. No, it increases to 169. And suddenly this histogram here is starting to look more like a triangle. So what's going on here? What happens if we add one more risk? So with 3 risks, what's going to happen? With 3 risks, it's starting to look more like a bell curve. And even though we want to be 95% certain, we're moving slowly closer to the middle. We're already closer to 200 than we are 300. So what's happening? Well, here I have all 3 risks all next to each other. And the answer is quite simple. But the answers lie in the nature of statistics, not in basic math. And again, all of these risks use a uniform distribution. All of them have the same minimum and maximum value between 0 and 100. And we just want to show how these financial impacts aggregate and how this all works. And you can see that the 95th percentile that we're reporting on starts to move closer and closer to the middle. And this is because we're dealing with the laws of probability. This is why we don't just add these individual risks together. This is why we don't just sum the values at the 95th percentile. And why does it work this way? Hopefully this example will be easy to understand, but rather than using data, let's just use some dice. And unless you're using weighted or magic or loaded dice, there's an equal chance to roll a 1 as a 2 as a 3. I mean, it's all equal. These are uniformly random. Now, if we roll 2 dice, something interesting starts to happen if you want to sum the total together. Even though each dice is independent from each other, when you combine 2 of them, you start to see that sum totals are more likely to occur. You're much more likely to get a 7 as a 2 or a 12. And that's because there's a lot more combinations that will get you a 7, whereas there's only one combination that will get you a 12 or a 2. We only have 2 combinations that will give you a 3. You get the idea here. And what I've done here is I've also just put in percentiles just to kind of show you what's going on here. Again, the percentile gives you a level of certainty. I mean, we can say that we are 83.5% certain that we're going to get a 5 or smaller result. And if we roll 2 dice, we can say that we're 83.33% certain that we will get a 9 or smaller if we roll 2 dice. And you can see that these are not necessarily, you cannot just double this. If we go from 1 to 2 dice, this doesn't become a 10. This actually becomes a 9. So I just want to show the same example using software. And what I've done is I've stuck with that same level of certainty, 83%, because we have 2 dice here. I mean, that's the same as 5, 6. So it's like rolling a 5 or smaller. And since we have software, we can start to make things a little bit more interesting. I mean, here's our example with 1 die. Here's with 2 dice. But we can take it up a notch. We can make it 10 dice and see what happens. So with 10 dice, you can see here our value at risk is 43. I'm still using that same confidence level, 83%. And if you remember, when we started with 1 dice, a 5 was our value at 83% certainty. 2 dice brought it to a 9, which is, if you divide it by 2, that's like 4.5 average per die. Now we're down to, for 10 dice, the average is about 4.3 per dice. Let's just turn it up another notch. Let's take it up to 40 dice. And you can see that the average here If we take 149 and we divide it by 40, we get 3.75. So again, the average per dice keeps getting smaller as we roll more of these up. It just keeps dropping. And the reason, again, is that there are many more combinations that can occur towards the middle than towards the edges. So if we go back to that single die example, where we were 83% certain that we would roll a 5 or smaller, if we were to sum a 5 for each of these, we would get a value of, well, that would give us 200 if we roll 40 dice. And you can see on the histogram, you don't see anything even close to 200. You can forget about rolling a 6 40 times in a row. I mean, that would give us a value of 240. But even with 100,000 samples, it's not like there's many outliers there. I mean, it's almost like 170, 169 is the upper limit of what we can get. So it's not even like we're seeing fives being rolled 40 times. And what I did was I did some back of the napkin math. I just wanted to come up with the probability of rolling a 6 40 times in a row. And these types of numbers are why they invented scientific calculators. I mean, my math might be a bit off. Feel free to correct me in the comments, but I'm pretty sure this is accurate, that it's almost statistically impossible to get a 6 40 times in a row. Even just getting a 5 or a 6 40 times in a row is just astronomically unlikely. It's very, very unlikely. And that's kind of the point here, is that we cannot aggregate a value at risk this way. We need to use simulations for that. So moving back to the risk world. So we're moving away from dice for a minute. I just want to talk about why this is the best way to aggregate value at risk, that you do it for the entire organization, and then you break it down by business units. And this might seem counterintuitive because it actually is backwards to how most aggregations work. If you are aggregating revenue, for instance, you roll it up. You start at the lower business units. That's where you have your data, and you roll it up to the top. But with statistics and risk, that is not the correct way to aggregate. If you were to calculate the value at risk locally and then aggregate, you will skew the numbers. And you can see that difference here. In the upper part of the screen, we are running all the risks within a single scenario. And these are everything here, all these values are set for 95% certainty. And you can think of them as millions or whatever unit, it doesn't really matter. But the point is we're trying to be 95% certain. And then what we do is we're breaking out the risk contribution by business units. So this, if you look here, we have 624 for the overall value at risk. This is precisely where that 624 comes from. If you add this up, it should be 624. The lower part of the screen illustrates what happens if I take these exact same risks that we just saw, and rather than aggregating them as a group and then breaking them up by business unit, I am only selecting at these different levels. So I'm using USA, GHS, this group OTE, this group thing. I'm using those individually, like different sets of risks here. And then I take these values at risk for each one of them and I sum them. And you can see I get a significantly higher value. I get 887 versus 624. Now, part of it is there might be just a few risks at some of these local levels. So that's also why these histograms look a little bit strange, because you're getting a lot of zero values and so on. But that's really beside the point. It's the point is that it skews the data. The same principle applies regardless. But of course, you will end up with more outliers when the groups are smaller, which push the values at risk higher for each level. I realize some companies use this approach, and there might be some valid reasons for doing this, but the calculations will always be higher than if you take the whole risk portfolio into the simulation. And the same thing would apply if you use risk categories. Like if you have your risks broken up by, I don't know, things that are financial, things that relate to environment, or just the different categorizations or taxonomies for the risks. The best way to do it again is to run these simulations as a large group, and then to break them up either by categories or business units and so on. All right, we've covered some of the basic stuff about why and what. I'll just get into a few other details with Monte Carlo and some other topics that I think are often confusing. One of them that you may have heard of is called distribution. And what is a distribution? I think it's just a fancy way to describe how random numbers are generated or distributed. Distributions are normally used on the risk impacts. So they're used for modeling the potential financial loss associated with the risk event. And here's an example of how those random numbers are generated based on 4 different distribution types. As you can see, the uniform is what we've already discussed. It's what people normally think about when they think about random numbers, where there's an equal likelihood of getting any of these values. But risk experts are not satisfied with just this basic uniform random values. So we have other distributions as well. This one over here, this is the normal distribution. And, where a uniform has a minimum and a maximum, a normal distribution is actually defined by the mean, which is an average, and the standard deviation. So you don't really have bandwidths. You don't have a minimum or a maximum. I mean, I think if you want to be precise, I think the minimum and maximum are kind of unknowable in a normal distribution. And then down here we have a triangular and a PERT. And these have an extra value. In addition to the minimum and maximum, they have sometimes called the most likely, sometimes called the expected value. If it's in statistical terms, it might be called the mode. But the idea here is it is a value that is most likely, and that can kind of skew this. So instead of having maybe a triangle where the peak is in the center, the peak might be closer to the maximum. So I have 2 different distributions with the same kind of inputs. Showing more detail here, but the minimum is 0, the maximum's 100, and then I've put that expected value at 80. So you can see here 80 is the peak, and you can see it's just linear. It's just pretty much a line up, straight line up, and then a straight line down. So that's a triangular distribution. And then there's also, it's kind of a similar concept. It's called a PERT, and it uses the same kind of inputs. We still have this minimum, maximum, and expected value, but it's a bit softer. You can sort of see that instead of it being entirely linear up and linear down, it's kind of gentle going up, and it's even a little gentler going down. To me, it looks a bit like a whale in a way, but it's the head and the tail are a bit more rounded off. These are often used for project management risks. But anyway, back to value at risk, and let's just start to put it all together. As we've said, Monte Carlo is based on using information that we know, combined with substituting random values to represent information that is unknown. And this is a bit of an abstract concept since it involves statistics and probability. But I just gave a brief summary of how probability works, and hopefully it makes sense. You understand why we use this approach. And one important thing to keep in mind is just to remember that we are not trying to predict which specific events will occur. We cannot predict these. But based on the laws of probability, we know that some risk events actually will occur. And we know that if they occur, there might be a financial impact. But again, we don't know exactly what that financial impact is. So we're modeling it usually on a bandwidth. So we simulate that data as well by using random values. Now, Monte Carlo can also simulate positive financial events. We've been focusing on risk, but we could include things like opportunities, like business opportunities. Or you can also use it to model things like sales or other positive things. So it's not just for loss, but for now, I just want to keep it simple and focus on the risk side of things. And before we get there, we should probably discuss probability. The probability is used in simulating whether or not the risk event occurs. If we say the probability is 30%, the risk event will occur in 30% of the simulations. So if we run 100,000 samples, it will appear in 30,000 of them. Since we are discussing risk events, then we use these random events to serve these two purposes. First, to simulate whether or not the risk event occurred, and then secondly, to simulate the risk impact or the risk lost. If we were making a Monte Carlo simulation to work with a portfolio of investments, for instance, we would not use probability at all because we know the investments will have some sort of price. But in the risk world, things are a bit different. We don't really know if the risk event will occur. And so that's why we use the probability. And then that also is used to show the different combinations in which the risk events occurred, which is like the different combinations of when you roll dice, for instance, like we saw earlier. So again, the values at risk applies to a portfolio of risks, like a big group of risks, literally hundreds of risks in some cases. And by using probability, these risks will occur in all sorts of random combinations. So in this example, project cost overrun will occur in 30% of the simulations. Labor disruption will occur in 30%. Sometimes they will occur together. Sometimes they won't. Sometimes just one will occur. Sometimes just the other. And that's just two risks. But if we have hundreds of risks running through, we will have countless combinations of risks that occur together. And I think a better way to look at this is to twist the table that we saw previously. So in this example, like in each row represents one of the iterations or one of the samples of the 100,000 samples that we will run in a simulation. And the way it works is like this. If we say that, in this case, that the probability is 15%, we will generate a random value. And let's say that value is below 0.15, then we say that risk is said to have occurred. And then if we say that risk occurs, we will look at the distribution and the bandwidth. Looks like we have probably a triangular distribution here. For instance, we get a value of, the impact is 18.1 for this risk event. Then we say these risk events did not occur, these did not occur, but this one occurred and this one occurred, and we will sum up those that have occurred, and we will do that for each row. And these values will be all over the place because we're doing, like I say, 100,000 of these iterations. And to calculate the value at risk, what we do is we specify that level of certainty. So if we want to be 95% certain, we will take all of these values together and we will rank them. So what we will do is from smallest to largest, we will look at the value that is at the 95th percentile. And then that value we can say, we know with 95% confidence that basically 95% of the values are at that level or less. And that's how it works. So in this example, I just have I'm just trying to show a little bit more how this would look. we have a bunch of risks. This is only a partial list of the selection table. You could think of these values as being in millions. They might belong to different risk categories, different business units. They might have a variety of distributions. And when you run them through, the results look like this in a histogram. And as we've said, that here we know that 95% of the values are less than our value at risk, are less than 88 million. So, which means, again, we're 95% certain our value at risk is 88 million. And we can also break these down into other types of percentile tables. So, I mean, we were at 95% certainty. You can see that we're at 88%. If we want to be 90% certain, we're closer to 80. At 80% certain, we're at about 70. So you can sort of see how the data fits together at different levels of certainty. And we can also rank all of these risks at different levels as well. It's probably more useful, though, to organize them like this, where we look at the contribution. And to look at the contribution, what we do is we look at risks at our level of certainty. So if we want to be 95% certain, we will look at the risks by business unit or the risks by category at that percentile. And we can show the contribution. I have this showing in contribution by percentages, but you could also have kind of the raw number, the actual how many millions they contribute to the overall value at risk, either way. And if you go to lower levels of certainty, some of these orderings and groupings might change a bit. Okay. I think that's a kind of a brief overview, and I did show a bit of Monte Carlo in our solution, but I want to just discuss software briefly. Now, I am a bit biased since I work for a software company, for a corporator that does this, but these sorts of calculations and visualizations are much easier when you're using software. I mean, you can make a basic Monte Carlo model in Excel, but it can be challenging to get it to work with hundreds of risks, or if you want to run like 100,000 samples per scenario, it's probably easier to work with 10,000, for instance. But if you do use software, you should probably consider some of the unique aspects about working with simulations. I think one of the things that you should consider is that this tends to be a bit of an iterative approach. And as we discussed, it's best to do these at the highest level you can within your organization. And that means that if you spend a lot of time selecting and deselecting risks out of hundreds of risks, you need a way to reuse your selections. You need a good way to search for risks or filter and find exactly what you need. Even if you have good business rules in place to say that you only have risks above some certain threshold, that might not be enough, because you might inadvertently be duplicating risks or omitting risks. So I think that's a key point. Also, I think you should consider integrating the whole value at risk aggregation just within the current risk framework that you use, because it gives the operational risk reporting process more context. And it also automates and streamlines the reporting process. So if you have to report to value at risk to the board or to the audit committee or other stakeholders, it's just all in there in an integrated process. And then, of course, it's also useful to have a rich library of visualizations, especially if you want to include these visualizations in your annual reports. So you have more than just histograms, but contribution charts, tables, maybe top 10 lists, top 5, top 3, whatever you need to better communicate with your stakeholders or your risk community. And then just some parting thoughts as I wrap this up. I've focused on the basic concepts, mainly to create some understanding and awareness of how value at risk is calculated. But there are many advanced concepts that I've omitted. And one of them is grouping risks that can occur together, or mapping dependencies or correlations among risks. For example, if one risk event occurs, another is more likely to occur. Or you might have the inverse, where you might say if one risk event occurs, it's impossible for another to occur. These are some concepts that are out there. Another concept that I touched on is the concept of opportunities, which opportunities are basically the inverse of risks. They're kind of the opposite. They're the positive events. And they can often be quantified as well and included in simulations. And I'll see that with some customers where it kind of offsets the loss